Unit 3, all the content is still there. We just don't know exactly when we're going to be assessing it. So let's carry on with some Unit 3 content. Yesterday, for most of you, we derived what the change in flux looks like for a loop of wire spinning inside a generator. Inside a magnetic field. And our name for this is a generator, for reasons that we'll see soon. And this is actually the main way that we get electricity. So the mains electricity that comes out of your PowerPoint comes from basically a big coil of wire spinning inside a big magnet. And what we got was, we got a flux, which, because it's all about the angle between this area and this magnetic field, turned out to be a sinusoid. So it looked like a sine graph. Then we applied Faraday's law, and we took the negative gradient of that function to get something that looked like this. And then we managed to sort of work out an approximation for the scale here by looking at a single quarter turn. And we found that the value that you get there is 4 NBAF. So when you use a quarter, 1 quarter rotation as your approximation, you get a change of BA for N loops in a time of the period divided by 4, so a quarter loop. And that gave rise to this scale here. So the average value of these peaks is 4 NBAF. We don't know what the exact value is, but that gives us a general sense of how much voltage we're getting on average. Okay, so today what we want to do is we want to take this graph here and sort of actually interpret it back in terms of physical current. So at the moment, this is really just maths. And we want to say what is actually going on inside this current here, inside this wire here, and what does it mean for us to have a negative voltage. The second thing we want to do is we want to interpret that in terms of what we're going to call alternating current, or AC, is the word we're going to apply to that. And then lastly, we're going to talk about how do we actually physically come along and grab this electricity that's on here and put it into an external circuit. So, you know, if we've got a heater or whatever over here, how do we actually hook ourselves onto this thing and get that electricity out? It turns out we can't just physically weld our wires onto it or use crocodile clips for reasons that we'll get to in a moment. Okay. So any questions about what we're aiming for today? Good. Hopefully we should be able to get it in a tight half hour or so. Okay, so first off, how are we going to find the current direction through this loop? So we want to know, when we derive an EMF graph, that's telling us about potential, it's telling us about voltage. The units on here are volts. But when we look physically at a circuit, we kind of want to know which way around is the current going, right? And remember, when we use Faraday's law, the Faraday part of Faraday's law gives us the amount of potential that we get, but it's the Lenz's law part that gives us the direction. So we're going to apply Lenz's law to work out, let's say in this first quarter here, what direction is the current actually going around in that loop. Okay? And I'm actually going to apply Lenz's law in 2 different ways. We've done this before. You can think of Lenz's law in terms of forces, which is usually my preference, to be honest, or you can think of Lenz's law in terms of fluxes. But either way, Lenz's law, remember, is that nature hates you and doesn't want you to succeed. So if you're trying to rotate something this way, Lenz's law will come in and push you back and try and fight you all the way, right? And so you can think that's when you think of it in terms of forces. If you're trying to reduce the amount of flux moving through a loop, then Lenz's law is going to try and increase that flux. If you're trying to increase the flux, Lenz's law is going to try and decrease that flux. Okay, so Lenz's law is always going to fight you. So first off, I'm going to think of this in terms of forces, because that's the way I tend to think about this. So the idea here is you've got to make a distinction between what motion is being produced physically by you and what forces are being produced as a counter reaction to that. So we are physically rotating this loop like this. We are physically, we're in there with a gear or a, you know, you can imagine an oxen, you know, walking around in a circle, pushing this thing around, right? And it's not an electrical effect. It's a physical, you know, just a normal force pushing on this thing. So we are physically moving this thing around here. According to Lenz's law, we should therefore expect, I'm trying to think of a good color. We should therefore expect a magnetic force which is opposing us due to induction. So we should expect a force pushing down on this edge here, and let's call it FL for F lens. And since we're trying to push this side downwards, this side downwards, we should expect there to be an upward force on this side. So a torque which is opposing the torque that we're trying to put on this thing. Okay, well, that makes, thinking of it that way actually makes it really easy to see which way the current must be, the induced current, because if this is an induced force, it must be a magnetic force due to an induced current, which means we can use FBI on this thing, right? So we can just say, well, if I want a force downwards, which is being produced by a magnetic field which points to the right, I can then point my thumb downwards, my index finger to the right, and if I move that down into this view here, that means I'm getting a current going back into the page. So the current that we get must be pointing in this direction, which means it's pointing down on this side, and we could use FBI on that side as well and derive the same thing. And that means it's circulating that way. And so from our view, if we're viewing it from the top, that means it's looks like it's going clockwise. So clockwise from top. Okay. Can I just get some indication of whether that made some degree of sense? Some yeses, nos, thumbs ups.
Yep.
Sweet. Okay. Now that is far and away the easiest way to do this. Okay, to use forces and to think of it as opposing your forces. If for whatever reason you prefer to think in terms of flux, well then the way to treat this problem is a little bit more difficult, and particularly more difficult in video chat form. If I was with you, I could sort of do like a 3D, like this sort of thing. This is going to be hard to explain in video form, but I'm going to try. But please be generous, and maybe we might come back to it when I see you in person. The idea here is if you want to do this in terms of flux rather than forces, well, the idea is we have a magnetic field pointing this way. And at this moment, at the moment pictured, so here on the x-axis, here on the time axis, at this moment, we are rotating the loop and making it bigger. We're producing more face for that loop to hit. That means the amount of flux passing through the loop is growing. So more field lines passing through my palm than when it's like this. If the flux is growing, then Lenz's law says we're going to want to produce an induced field which points back that way. So as we grow, we're going to want to produce an induced magnetic field to balance out the growth of more and more flux from this field. So then we say, okay, our current is producing a magnetic field in the opposite direction to that field. So then we apply right-hand rule to that current, and then we try and flatten that out in our brains and put it on the page, and we realize it turns out to be the same direction as the force version. It's really hard to think about, though. It's really difficult. It's really difficult in person, and it's even more difficult in this format. But you can do it that way if for whatever reason you prefer. My strong endorsement is to do it in the force way, though. Now, as we continue to rotate this thing.
Wait, sir.
Yes.
So when finding the induced current, I also realized that the whole motor is rotating clockwise. So is it always like in the same direction, or would it change?
You've got to be, because we're in 3D, clockwise doesn't necessarily mean clockwise, unfortunately. So the motor is rotating this way, clockwise, but the current is rotating this way, clockwise. So they're at right angles to each other. The clockwise current in the motor is like in that dimension.
But like if the motor were to go anti-clockwise, then wouldn't the forces swap? And
Yes,
like
absolutely.
the
Yes,
induced
absolutely.
current would go the other way?
That's absolutely true. I want to warn you against trying to apply some general rule, like if the motor spins clockwise, the current goes clockwise, because you're bound to encounter some situation where, I don't know, the magnets are the other way around, or the flux is the current, the EMF is defined in the opposite direction, negative, positive. There's all sorts of things that can go wrong with just trying to have a blanket rule.
Okay.
Including, to be honest, if we just looked at this, if we just drew this 3D diagram from a different perspective, then we would get a different answer.
Okay.
So we really do need to think about the forces and then say, okay, what current would produce a force which would oppose us?
Okay.
Okay. I mean, you can try and sort of write down every possible situation and say, in this situation, clockwise, clockwise, in this situation, anti-anti. But I suspect it might just, you're going to be more parsimonious to remember one way of doing it rather than trying to remember all the different combinations.
Yeah.
Okay, so that's the way we're going to find the direction of the current. Now, of course, when that current gets to 90 degrees, there's going to be no EMF in there. So when we have maximum flux, that's when we have, at 90 degrees, that's when we have no EMF at all. And then notice that the EMF then it flips sign. It goes from being negative to being positive. Right? And so what does that mean? Well, this argument here about the forces, that bit doesn't change. So if we flipped it 180 degrees, when we get over to this side, it's still going to be the case that those forces are going to point in those same directions, still trying to oppose us from rotating this thing clockwise. So what has changed? What has changed is the direction, and if you were to draw the picture 180 degrees later, the picture would look exactly the same. The current would still be going clockwise. Right? The current would still look like this, only the loop itself would be flipped over. But a loop flipped over looks exactly the same as when it was there originally. So what has changed? When we say the sign of the potential has changed, what has actually changed? And the way to think about this is that, well, where is our voltmeter? Our voltmeter is connected to the ends of this loop. And even though the current is still in the same direction as before, and the forces are still in the same direction, and therefore the potential looks like it's causing a current in the same direction, these two prongs of our voltmeter have actually swapped positions. So where we're measuring the voltage before we had our 2 prongs, positive and negative, now it's positive and negative. So the red one has gone from being positive to negative, and the orange one's gone from being negative to positive. And then 180 degrees later, they flip back again, and now this one's positive and this one's negative. Now this one's positive and this one's negative. So a bit like with the when we're talking about DC motors, the right hand side here is always going to be the positive. Is always going to be the. Oh, sorry, I got that the wrong way around. The left hand side is always going to be the positive because that's where the current's coming from, and the right hand side is always going to be the negative because that's where the current is going into. So we can also sort of put that on a diagram that this end, whatever part of the wire happens to be on this end, is always the positive terminal, and whatever part of the wire happens to be on this end is always the negative terminal, because those are the current directions we've derived. Okay, but in terms of physically putting a voltmeter on there, that they're going to keep flipping directions because these two terminals keep flipping positions. It's a little bit hard to get your head around, but you will eventually. If you watch the Ed Raleigh videos and stuff, you'll get the idea there. The idea is that even though the picture stays the same, the actual physical wire positions swap. So the current that was going backwards in this wire here, when it gets to this side, will be coming forwards. And then when it flips to 180 degrees again, it'll be going backwards again. So any given little bit of wire here is going to have currents going backwards through it and then forwards through it, and backwards through it and then forwards through it, and backwards through it and then forwards through it. The name for that type of current that goes back and forth instead of in a continuous direction is called alternating current. Okay, so do I need to write that down as just a bit of notes? Inside the generator, so I'll just read that. Inside the generator, what we're producing is an AC current. So that's a current that's driving forwards and then coming back, and driving forwards and then coming back. That sort of current is reversing its direction each cycle. So it's going one way for half a cycle, then it's coming back the other way. It's going one way, it's going back the other way. And it's going to be a sinusoid just like the potential. So if you think about V equals IR, we start to sort of, V equals IR starts to become not so true once we talk about alternating currents, but for the moment, let's imagine it is. The current and the voltage are just linear relationships to one another. You just multiply by R. So if the graph of voltage looks like this, then the graph of current is just going to look like that divided by R. So that means the current, we can no longer just say, oh, it's 3 amps of current. We have to say the maximum current is whatever that is, the amplitude, and it's oscillating with a particular period. All right, so just like AC voltages, these voltages that we're generating here, these EMFs, are non-constant, the same is going to be true of the current that's in there. And just as these potentials are going negative, positive, so too are the currents going to be going left, right, left, right, left, right. Okay. Are there any questions about that just conceptually for the moment? No? Okay. All right. So the last issue we have, before I let you go, is just checking the time. The last issue we have is that if we think about this loop, and I'm not going to bother drawing the magnets now, But if we think about this loop rotating, and let's imagine we want to use the electricity in here to run our toaster. I've got toast on the brain because I didn't have breakfast this morning. Woke up too late. So, I don't know. Here's our toaster. Okay, we've got a toaster. And can anyone see what the problem is if we would just clamp these wires straight onto the poles of our, this thing here is called an armature. And
they'll get tangled up.
Yeah, they'll get tangled up. Fantastic. Right. So if we just crocodile clipped on these wires, well, then after a few turns, they're going to get twisted and twisted and twisted and twisted and twisted, and they're going to become useless. Okay? So we need a way of getting the electricity out where we have these armatures, where we have the armature connected, electrically connected to our toaster, to our load, to our external circuit, but not physically connected. Now, we've already seen one way of doing this. What is that way?
Like using the brushes?
Sorry, two people talked at once. What was that, Jai?
Using those brushes, the commutators?
Fantastic. We could use a commutator, right? So one way we could achieve this is we could use a split ring commutator. Okay, so a split ring commutator, remember, was, I'll draw it in black because it's the important part here, right? Was like a little piece that looked like this that was connected to the armature and spins with the armature, and then connected to the load, we have these carbon brushes that just make contact not with the wire themselves, but with the commutator. All right, so this thing here is a split ring commutator. So let's go. So this diagram here is going to be of a split ring connection. So we've got a split ring commutator, and the idea here is this little loop thing is free to rotate, but it's going to remain in contact with our carbon brushes, right? Because the carbon brushes are kind of soft, they give a little bit, and this thing here rotates fully, and it sort of takes up the full 360 degrees of space. So you're never disconnected. Okay. Now, of course, we'd have a short circuit if we didn't insulate the middle here. So we don't let any current sort of cross from one terminal to the other directly. We always have one semicircle is connected to one terminal, and one semicircle is, welded onto the other terminal. Okay, so the whole thing just spins together with the terminals. That means this brush here is not always connected to any one of these rings. Sometimes it's connected to this ring here, and then the whole thing rotates, and it will be connected to this one over here. So just like exactly the same as the DC motor, the exact same setup, except instead of us pumping in energy using a battery over here, we now put some sort of resistor over here, and we pump in the energy by actually doing work on this system, by rotating it physically, right? Okay, now one thing we could ask is, what does the current that we get in this circuit actually look like? Now, remember that no matter at what position in its rotation this is in, this side here is always feeling a force downwards, and this side here is always feeling a force upwards. That means the current on this side of the loop whatever part of whatever physical bit of the loop actually happens to be on the left is always going to have a current in this direction. And whatever physical part of the loop happens to be on the right is always going to have a current in this direction. So that means whichever part of the loop physically happens to be on the left is always going to have the positive charge on it, is always going to be the positive terminal. And whichever part of the loop happens to be on the right will always be the negative terminal. So that means when this bit of let me color code these. I'll make this side of the loop pink and this side of the loop black. Ooh, starting to look a bit like a Pokemon ball. When the black side is on the right, it's going to be negative. But when it spins around and finds itself on the other side, at that point, it's going to be the positive side. When it spins around further, it's going to go back to being negative, then it's going to go back to being positive. So that means this carbon brush here is always going to be in contact with the positive side. And this carbon brush here is always going to be in contact with the negative side. So we're not actually going to have AC electricity coming out the other side. We're going to have electricity which is always going from positive in this direction. So I external is always going to be going in this direction. Now the magnitude of that current is still going to be bouncing up and down as a function of the magnitude of the potential, but the direction, just like in a DC motor, the direction gets changed every 180 degrees by this split ring commutator to keep it constantly positive. So if we were to sketch current versus time for this circuit, we actually get something that looks like this. So it's not DC in the sense like a battery produces where it's a nice straight line, a constant amount, but it's DC in the sense that it's always going in the same direction. Okay, let me quickly just write what this split ring commutator does. The split ring commutator takes the AC electricity in the armature and there doesn't seem to be a good like formal wording for what the split ring here thing does. So you often see words like flips and switches and stuff like that, and I don't really have a good like technical terminology for it. But in the armature and flips the direction, or flips the polarity maybe, flips the polarity every 180 degrees, producing a DC output. Okay, is that on your screen? Can you see that? I've got things covering it up, but I think it should be visible to you. Okay. Do you want a moment to take down those notes before I show you the other way of connecting?
I'm fine.
You're fine? Is anyone not fine? Okay.
So
all right.
if you put a magnet around the circuit, not the armature, but the circuit with the ammeter and stuff, will that spin as well?
Ooh, good question. Yeah. Well, you could. This would become a DC motor. So you would. Yeah. You could have a generator driving a motor, but the problem is that because the current's always going in the same direction, you have that problem that we have with the DC motor where it would go up to, it'd get to that point there and then it would just go chick, 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 chick. Because we need something, once it gets to that point there, we've got a force going this way, we've got a force going this way, force going this way, force. We need something to flip the direction so that we then have a force pushing it down on the other side. So directly putting magnets on this will produce a motor, but a faulty motor. The next version we do, it really will be able to produce just a straight up motor. That'll be maybe an interesting problem. Okay, all right, I might move on to the other way we can connect. Okay, so this is the way we connect if what we want out is DC electricity. So you could imagine if you wanted to run a computer, you would want DC electricity for that. So you would use a split ring commutator here if you had a little generator running your computer. Obviously you don't use mains electricity, but let's say we did. The other way to connect, which I know means I have to draw again. The other way to connect is the way we're going to connect if what we want out is AC electricity. So if what we want in our toaster is AC electricity going through, so we want electricity which keeps switching direction, which I don't know, maybe you do for whatever reason, then we're going to have to connect this up differently. Okay, and this way I find really clever, but may test the limits of three-dimensional thinking in Zoom. Okay, so we've got our armature here. Got our armature, and we have AC electricity in here. So inside here, if we were to just put a voltmeter on the ends here, then what we would get, remember from before, we had something looking like this, and that was, so we had an EMF going back and forth. So this is inside here. So what we want is we just kind of want that. If we want AC electricity out, we just want that, please. We don't want we don't want to change any polarities. We don't want to be splitting it every 180 degrees. We basically want to be able to put this wire here in constant contact with that terminal there. And we want that wire there to be in constant contact with that terminal there. It's almost like we want to be as close to just putting crocodile clips on as we can. Because if we could just put crocodile clips on, then we'd get this output. But crocodile clips will get all tangled up and that'll be a problem. So what we use is a slip ring connection. At this point, I would like to apologize on behalf of engineers everywhere that the two names for these things are so freaking similar when they have completely opposite function. There's nothing we can do about it now, but for if we want AC electricity out, we use a slip ring. If we want DC out, we use a split ring. The sort of the nice way to distinguish and make it clear that you know what you're talking about is to always, for the other one, for the split ring for DC, you always call it a commutator. For this, just don't use the word commutator. Okay? Okay. So here's what we do. And in order to show this, I'm just going to draw a little side-on view. So the loops over here off screen to the right, and here are the armatures coming out. Sorry, here are the terminals coming out. What we do is we actually make one of the arms much longer than the other. Okay, seems a little bit silly at first, but I assure you that's a good idea. Then what we're going to do is we're going to insulate a little bit of this longer arm, right? So we're going to put some electrical tape around it. That's not actually what they do in generators, but for our purposes, let's just put some electrical tape around it. So we're just going to insulate this little bit of the arm. Okay, interesting. Why would we want to do that? Then what we do is we put a little circular loop oh God. A little circular-ish, little circle, little circular loop like this, where this arm is rotating inside. Right, so making contact with this terminal here, also maybe making contact with this one, but it's insulated anyway, so who cares? Then we put another little loop over here. Making contact with this one. That's what I'm looking for. Three-dimensional styles. Not my best picture I've ever done, but okay. So what we have is two little loops that our wires are spinning inside of. Right? So as the armature spins, these wires are spinning inside these two loops. The long one is spinning in both loops, and the short one is spinning in just one loop. So what that means is this short one is always in contact with this loop. This long one is not electrically in contact with this loop because it's insulated at that point, or you find other ways to stop them from touching each other, but it is always in contact with this loop. So this is equivalent to being able to just crocodile clip onto these things. We have one side of the circuit which is always connected to one of these terminals, and we have the other side of the circuit is always connected to the other of the terminals. So let me just kind of put this onto the drawing. So what we're going to have is this slip ring here. This kind of has to get around up both of them. Really lost my drawing touch today. I apologize for that. Okay, so we have these things here called slip rings. Right, we also put some carbon brushes inside those slip rings so that we've got a bit of give and a bit of softness for it to make that contact better. But the basic idea is that one of these terminals will always be in touch with one of the slip rings. The other of the terminals will always be in touch with the other of the slip rings. And so as they rotate, one of them always just gives its electricity to one side, one of them gives it to the other. So that means the output we get in terms of current, if we put that, a current and ammeter there, is just a straight up match for the EMF that we're producing in the loop, because we're just directly connecting to it. There's no flipping every half turn or anything like that. Okay, so this produces AC electricity through a direct connection to each terminal. Okay. Does anybody have any questions about that? For at least a couple of weeks, you're going to get these two confused. Slip ring, split ring. They're very similar names. Slip rings But the way to remember it is slip ring is the one where it slips through. So the long arm slips through the short arm, the first. Now, in answer to Ricky's questions from before, now if we put magnets around this loop here and got it spinning at the same rate that this was spinning here, you could have them going together. So this current here, this generating over here, so we'd be winding our handle over here, that would be spinning this, creating electricity, that electricity would go into this one, and then that would become a motor. So you could have a generator driving a motor. And of course, every electrical motor in your house, so your vacuum cleaner, your washing machine, your dishwasher, all of those have motors in them. That's exactly what's going on. There's a big generator sitting in the Latrobe Valley burning coal, spinning around and around, and it's sending electricity down the lines, and then that's driving a whole bunch of little DC motors and AC motors in your electrical appliances. Okay. Now, well, I was about to say you might wonder, but is anyone wondering anything?
Why is it important that some things get like AC electricity and some things get DC?
Fantastic. I think they're actually kind of like weird bit of trivia, but I think they're currently making a movie about this.
Wow.
Which sounds very dry, but called The Current Wars, which is basically when they first invented like large-scale electrical systems, when they first worked out they could do this with generators, the two big people involved were Thomas Edison and Nikola Tesla. And Nikola Tesla was a fan of AC electricity, and sorry if I mangle the directions on this, a bit like a split ring and a slip ring. It's one of those things that's hard to remember. And Edison was a proponent of DC. The advantages of DC are that with a slight modification, you can turn this sort of DC into pretty flat DC, like a battery. So by putting in some capacitors into the circuit, and a capacitor is like a little storage unit in a circuit, you can turn this, you can sort of shave off the peaks a little bit and make this a little bit more like this. Right. That means that anything that's been designed to run on a battery, you can pretty easily use DC electricity to run that. So anything that needs a pretty constant amount of electricity, so if you think about a laptop, it needs a very specific voltage in order to do quite precise calculations and so forth. And you can't just give it like wildly varying voltages. So DC is better for running electronic equipment. On the other hand, AC, and the reason with that in mind, the reason we use AC and the reason Nikola Tesla won the current wars, so the electricity that's coming through your power points is AC, is for two reasons. One, this sort of situation is much more stable. It doesn't degrade as quickly. It's simpler. You just have two rings and they just sit there. You don't have this sort of fancy commutator thing that can go a bit wonky and like you can get the timing slightly off and it might be at 169 degrees rather than 180 degrees and things like that. So slip rings are more sort of simple and stable. And in electronics, one of the absolute key things is keep things simple, because the more things you have, the more failure points. But the bigger reason is what we're going to get to in a week or two's time, which is that AC electricity, it turns out, is really easy to change the voltage of. So if you produce AC electricity at 10,000 volts, it's a really simple process to bring that down to 200 volts, or to push it back up to 5,000 volts, or to change the voltage up and down, right, using these things called transformers. DC electricity, much harder. Similarly, if you have AC electricity, it's pretty straightforward to turn it into DC electricity using either a split ring or a diode. Remember, a diode is a thing that only lets electricity go one way. If you have DC electricity, turning it back into AC is actually a pain in the ass. So if any of your parents are like into camping, they probably have an inverter on their car, which turns the battery power into like mains electricity. That's got to turn DC battery power into AC electricity for like things to plug into. And you'll notice two things. One, they're really expensive. And two, they're like really inefficient. So you blow through your car battery really, really quick trying to run AC equipment off it. But yeah, we'll talk a lot about the advantages of AC next week. Generally speaking, we made the right decision. Like, it was good that Tesla won. AC is the right way to go for large scale generation. Any other questions before I let everyone go? No? Okay. All right. All right. So sorry if I yammered on a little bit quickly there. Feel free to watch the video back. And I suppose I'll post it up, and that way you can grab the notes later if you didn't quite grab them. Okay. All right. I'll see you all later. Keep up the questions in the Discord. Keep up. There's lots of interesting questions coming in, which is good to see. Possibly on things that'll be cut from the study design. I'll let you know when I know more about what's happening there too. Okay. See you later, guys.
Thanks, sir.
Do we have a home group?